Let's revisit an idea that is something acidic or basic? Possibly neutral. We'll see. But in a lot of our cases, when we looked at this before, we actually had something that was strong and maybe something that was weak added with it. Or one of the counter ions was something that was from a strong acid or a strong base. Like, for example, in this first case, if this instead of being ClO2 was just Cl, then that would have come from HCl. That's a strong acid. And we would know for sure that this is acidic, right? Because our counter ion wouldn't have any appreciable acid-base properties. However, in this case, both the cation and the anion have acid-base properties. This ethyl ammonium is a weak acid, and this chlorus, or let's see here, chlorite is from chlorous acid, which is a weak acid. So this is a weak base. That's a weak acid, weak base. So is this salt acidic or basic? Well, it's very difficult to tell just by looking at it. We actually need to look at the Ka and the Kb of what we have here. So let's do that. If we look up in a table, we might only find the Ka for chlorous acid, which in this case is 1.1 times 10 to the minus 2. But this isn't the acid, we're looking at the base, so we'll need to look at Kb. Fortunately, we can calculate Kb from Ka by taking Kw, 1 times 10 to the minus 14, divided by Ka, and that will give us Kb. And in this case, we get a Kb of 9.09 times 10 to the minus 13. So I'm going to write that right here. ClO2 negative Kb. That's one of them. Now we need the Ka for ethyl ammonium. The acid. And that Ka is 2.12 times 10 to the minus 11. Both of these are quite weak. This isn't the best acid, and that's not a very good base. But now we can answer the question. We need to know which one of these is better at its job. Now, this is times 10 to the minus 11. That's times 10 to the minus 13. So, this is a larger number. That means I have a better acid in this ion right here than this one is a base. So this first salt will be acidic since the acid is a little bit stronger. It has a bigger K. And again, we need to compare the Ka to the Kb. So make sure that you have the Kb for the base and the Ka for the acid. Now, on this next case, you'll notice that I've switched the anion from ClO2 to just ClO, which is the hypochlorite. Now, if we think back a ways, you'll remember that if I reduce the amount of oxygen on here, then I'm going to concentrate the negative charge on the oxygen, and it will be a little bit weaker of an acid. And so it'll be less likely to give up its proton. So let's see what effect that has. So if this is a weaker or a less good acid, the conjugate acid is less good, that will probably mean that the conjugate base is better because it's less likely to give up its proton. So it's more likely to pick one up now. Now the Ka for hypochlorous acid is 3.0 times 10 to the minus 8, which makes the Kb 3.3 times 10 to the minus 7. So this, the conjugate acid of this chlorous acid, is a much better acid than our hypochlorous acid. But since this is not a very good acid, its base is much stronger, and you'll see the Kb is much higher. Now, I still kept the same cation, so we can compare the Ka value right here. And you'll notice that this is now a weaker acid than this is a base. And so in this case, this solution should be basic. And that's because our Kb is bigger than the corresponding Ka. 10 to the minus 7 is bigger than 10 to the minus 11. Now, down here, I saved something for last. This is ammonium acetate. So this is ammonium acetate ion. So this is from ammonia and acetic acid. What would happen if we combine those two together? Now, it just so happens that the Ka for acetic acid is 1.76 times 10 to the minus 5. That's the Ka for acetic acid. And it turns out that the Kb for ammonia is 1.76 times 10 to the minus 5. The Kb for ammonia and the Ka for acetate are exactly the same value. Well, at least to how many significant figures I have. So Ka for the acetic acid, which this is not acetic acid, this is the acetate, but we can think about this, is 1.76 times 10 to the minus 5. And the Kb for ammonia is also 1.76 times 10 to the minus 5. Same value. Now, we can convert these to this one to Kb and that one to Ka, but since they both have the same value, we already know that the response should be the same value for Kb and Ka for the respective thing. Of course, it won't be 1.76 times 10 to the minus 5. It'll be something times 10 to the minus 10. But those values will be the same. So, what happens if we have a weak acid and a weak base that have the same value for their Ka and Kb? This will actually make a neutral solution since they're equally strong. And this is one of the ways to make a neutral buffer. And it's kind of an interesting case since the pKa's of both of these are nowhere near 7. But because they're both weak acids and weak bases, their counter ions or their conjugates have the same, they both have acid-base properties, and since they have the same Ka's and Kb's, they will end up making a neutral solution, or pH 7. And this is one of the standard ways of making a pH 7 buffer, is to make it with ammonium acetate. And one of the great things about that is that you can simply weigh out however much ammonium acetate you want to make whatever concentration of buffer that you want, and it will be at a pH 7 just by dissolving this. It's kind of a neat buffer system. It is also a volatile buffer, and so sometimes if you want your buffer to be able to evaporate, this is one that you can choose. And it buffers very closely to physiological pH, so it's pretty good for proteins and other sensitive molecules that you may want to buffer at a neutral pH. So, this is how to determine whether a substance is acidic or basic if both of the ions have acid-base properties. Simply compare the Ka's and Kb values of the respective ions. Make sure that you're comparing the Ka of the acid to the Kb of the base forms. And simply pick the larger value for the Ka or for the Kb, and that will tell you whether it's acidic or basic. If the Ka is bigger, that solution will be acidic. If the Kb is bigger, that solution will be basic. And if they are the same value, the solution will be neutral.